Hey, welcome back. This time and we're working with line integrals, and first we want to work with doing parallelizations of curves. So curves and their formulas, I guess. So let's look at this example one here. We already gave you a tool for developing equations of lines, vector valued equations for lines in space and in the plane. Here we have three lines that we're worried about, from 0, 0, 0 to 0, 2, 0 to, and then from 0, 2, 0 to 1, 2, 0, and then from 1, 2, 0 to 1, 2, 1. Okay, so C1 goes from 0, 0, 0 to 0, 2, 0. Okay, and the way we kind of taught you how to do this is to kind of get a slope. So the x slope is 0, the y slope 2 minus 0 is 2, the z slope will be 0. Orientation matters in this context, so you can't put like 0, negative 2, 0 and figure it's going to work. And then plus the initial point, 0, 0, 0. And you'll basically get the formulas that they have in the book here in their solutions. So rewriting it, it's 0, 2t, 0. So you see the first part, the first curve, 2tj from 0 to 1 over there on the right. So we nailed the first one. The big issue for us now is that they're kind of going to want the parameters to first, for C1, go from 0 to 1, and then for C2 to go from 1 to 2. Okay, so that becomes kind of annoying. Anyways, let's look at the curve C2. So I have 0, 2, 0, and I need to go to 1, 2, 0. You could do the same thing for the slope. So the slope here will be, 1, 0, 0. That seems right. Times t, and then plus your starting position is 0, 2, 0. The issue now, though, is I need my parameter to be a little different. I need to go from 1 to 2. And the formula I have likes the t value to go from 0 to 1. So to kind of change that, what you're going to have to do is to basically, if you just subtracted 1 from all three sides, you would kind of get it to work. Okay, so I'm going to do a replacement with t and just plop in t minus 1, and that will give me my formula. Okay, so I'm going to replace this t now with t minus 1. And so my formula will be t minus 1 comma 0 times t minus 1 is 0, but then plus 2, and then 0 times t minus 1 is 0, and then plus 0 is 0. So you see, and equation, the equation for C2 there, t minus 1, 2, and 0. Okay, and then C3, same sort of issue. It would be easy if we could just make the parameter go from 0 to 1, but they want it to go from 2 to 3 now. So anyways, 1, 2, 0 to 1, 2, 1. So my r of t this time, I kind of play the same game, but I'll use a t minus 2 on the outside here. So plus then the starting position, 1, 2, 0. The slope, so to speak, 0, 0, 1. And so our formula will end up being 1, 2, t minus 2. In all honesty, what I generally will do is just guess at these formulas. For some of them, they're pretty obvious. So like this first curve, r of t must equal 0, 0. So x is always 0, so I put a 0 there. 0 to 2. If I'm going from 0 to 1, I want it to be 2 at 1, and then just put a t in there. So when t is 0, you get 0. When t is 1, you get 2. And then finally the other guy is 0. Okay, so you can play that game. R of t in the second guy, so there's an issue with the first component. It seems like it just, but then you have to worry about it's 1 to 2, right? So you're going to have to go t minus 1, and then 2, and then 0. Okay. There are kind of programmable methods to use if all else fails. So for example, if you're doing your homework and you just cannot guesstimate it, you can't use kind of the vector equation of a line in order to figure it out, like that's failing you for whatever reason, I'll kind of show you what to do here. Okay, so for like number 2, you could just totally guess that one. For number 1, it's not even an equation of a line, right, for part of it. So the first part, they give you the formula is just t comma t. But the second one is this square root x. Okay, so normally so it's goes like this, and then it comes back around on this. So this c1 is the first part of the piecewise definition above for our r of t. The second component of that piecewise definition, C2, I need basically a formula, a vector valued formula for y equals square root of x, right? So y equals square root of x. Now normally, if we didn't care about the parameter, we could just use t comma square root of t, right? Because here x would equal t, and then y would equal the square root of t, but x is t, so we would have y equals square root of x, and we're back to where we started. Okay, that would be great, but unfortunately there's 2 things out of whack here. First, the parameter is out of whack. We want to go from 1 to 2. And secondly, we're not going in the red direction. That red arrow I just put there, we're not going in that direction. This formula right here that I've kind of produced right here, as soon as I get the marker to work, this thing is for going in the opposite direction on the curve. Okay, it'll start at 0, 0 and then go to 1, 1. Right, we want to start at 1, 1, this point here, and then go to 0, 0. Okay, so I need to remedy that situation as well, and you can kind of fiddle around with it and maybe just do some transformations like you did back in pre-calc, and you'll probably hit on it after a while. So it's going to be something like 1 minus t, because that will start you at 1, and then so when t is 1, that will be so maybe 2 minus t. Right? So when t is 1, that will be 1, and when t is 2, that will be 0. So you're trying to get those x coordinates to work. So that if in the first position I want 1, and then I want 0 when t is 2. Okay, so this is at t equals 0. T equals 1. I want 1, 1, and then at t equals 2, I want 0, 0. Okay. Very simply, we could just put in a square root right there, right? So t, and then we could see if we got it. So when I put in 1, I got 2 minus 1 is 1, and then the square root of 2 minus 1, that's the square root of 1, that's 1. And then when t is 2, I get 0, 0. So it seems to work, and you could see there to the right, that was my answer, and certainly it worked. Okay. For number 2, you can kind of just plug in values and see what works. You got to start at 0, 0, and then go to 5, 4. So you could pretty much just guesstimate which one works. Number 3, we're going from 0, 0 to 2, 4. You can almost guesstimate the vector valued equation for this. So if I'm going from 0 to 2, the first component, I need it to go from 0 to 2, right? So you just use t for that. And then the second component, I need to go from 0 to 4, so 2t. So it's like a bit of guessing, but like I said, there is kind of a programmatic way to do these jobs. Note I'm going from 0, 0 to 2, 4, and I need a vector value equation. I need an equation for x in terms of t. I need an equation for y in terms of t, right? And then these are the components that I'm putting in here and here. Okay. All right. So how do you do that? Well, the x components, I want to go from 0 to 2, and you kind of think of all of these as ordered pairs, right? They're components the ordered pairs are t comma x. All right, so I want it to go from where t is 0 and x is 0. And then the second point would be t equals, well, what do we want? We want 2. And then x we want to equal 2. And then you could literally just make an equation out of that using your point slope form from algebra. Okay, so the slope would be 2 minus 0 over 2 minus 0, which is 1. And then use your y, well, in this case it would be x minus x1 equals m times t minus t1. Okay, so you'll have x minus 0 equals 1 times t minus 0. In other words, x is equal to t, and of course that's what we got just by kind of guessing. Right? Okay, so the same thing with y of t. Your ordered pairs are now t comma y's. The y value you want to go from 0 to 4, right? So you go 0 for t, 0 for y, and you want to make that go to 2 for t, and then 4 for y. Okay, so again, this is t, this is y, this is t, this is y. So your slope would be 4 all over 2, which is 2, and then use your slope point form. So y minus 0 equals 2 times t. I'm using the first point. It's pretty easy. So y is equal to 2t, and of course, you know, we nailed it. Okay, so that's the programmable way of doing it. So if you're totally clueless and you say, well, how the heck is he guessing that? You could go through that every time, and you do that about 5 times, and you're going to say, I'll start guessing. That's fine. Anyways, there's other problems. You know, they're going to give you a whole, I mean, there's so many different versions of this problem. It's kind of hard to just give you one formula, one sort of, like they look for the God particle. We're looking for the God formula, you know, the one formula that gives you everything. I don't think so. It's like number 4 here. We're trying to parameterize this path C, x squared plus y squared equals 81, going from 9, 0 to negative 9, 0. So what the heck is that? You know, 9, 0 is right here. This is a semicircle like this to negative 9, 0. So you have to probably think kind of like a almost a polar type thing, you know. So x is equal to, well, you know, you could replace x with cosine, kind of, right? We would have to take this guy and solve for, bring the 81 over. So you have x all over 9 squared plus y all over 9 squared equals 1. And then x over 9, you could say, is equal to cosine of some, whatever your parameter is. And then y over 9 must be sine of your parameter. So x you could have as 9 cosine t, and then y is equal to 9 sine t. And to get the semicircle, you're just moving from 0 to pi for t. Okay. Yeah, there's no one God formula I can give you. 3-dimensional ones, maybe we'll hit on once we get more into the material. So anyways, once you wrap your brain around producing all of these curves with using parametric equations to produce the curves, we finally introduce the line integral. And so what you're dealing with is maybe some sort of curve in the plane or a curve in space, and you're sort of attaching values to each point of the curve. Okay, so it's almost easier to think of this in 3 dimensions. Okay, so you have some sort of curve maybe here in the xy plane, and then you can kind of think of this as going to be like a curtain type idea. Okay, so what you're going to be doing is kind of finding the area of that kind of little wall that's being built right there. But anyways, the integral will be f of x comma y ds, and they write it like that. So the integral of what exactly do they call it? The line integral of f along c. Okay, so this is going to be the line integral of f along c. So what the heck is this thing? If you look on the right and you have a space curve, what you're going to do is partition that space curve up into a bunch of little segments. Okay, I don't know what it's doing. Maybe it's looping around, doing whatever it wants to do. And right, so you're taking all these little line segments, and those will be kind of like distances. We'll say delta s's. Right, and then we're attaching to that little distance maybe some function in here, right? So from this little portion of the curve, we'll have some function f of x, y, z times delta s, and then we want to go all along this curve and just add those up, right? And then of course take the limit as and here they're going to define something, a partition type thing, or a norm. They're going to say we're letting this thing go to 0, and that thing, that delta inside of the double absolute values, that represents the longest kind of arc length in your summation. Okay, so if you let the longest one of those little line segments go to 0, it'll kind of force this into our form for the line integral. Okay. All right. How do we evaluate this thing is kind of a good question. First, recall the integral for arc length. So we had the square root of x prime of t squared plus y prime of t squared dt from a to b. If you take the derivative of that thing, you get ds with respect to dt, but the end result is kind of like the integral goes away, right? So you have the square root of x prime of t squared plus y prime of t squared dt. So what is that thing? That thing is the magnitude of the equation for that curve in space, right? So this weird crazy curve, the second one, so this is my first one. The second one I drew here, let's say the vector value equation for this is r of t, right? The magnitude of r of t is basically going to be ds, right? Because ds, this object right here, is just the magnitude of r of t. I mean, that's the two-dimensional version. You'll see the three-dimensional version here on the right in the book as well. But anyways, what you're going to do to evaluate this thing is to kind of replace that ds and the x and y inside of it. So you'll have x of t, y of t, where you're getting the x of t and y of t from the vector value equation for the curve, and then ds will just be the magnitude of the equation for the curve dt, and then you'll be able to evaluate that. Okay, so you'll see that in theorem 15.4. Okay, and this is the 2D version, and then there's also a 3D version, which isn't very different. Okay, but anyways, that's the issue. That's what we want. Of course, if f of x, y is just equal to 1, what you end up with is the arc length integral, which is what you see right here. But anyways, let's try to evaluate a line integral, shall we? So example 2, we want to evaluate this integral x squared minus y plus 3z ds. And first we have to go back to what we were learning how to do in section 1. We need to figure out a vector value equation for this curve. Okay, so they show you the curve, is going from 0, 0, 0 to 1, 2, 1. This one's easy, right? So it's just r of t equals t comma t plus 1 comma t, and that has a parameter going from t 0 first, so you get the 0. Whoops, if you plug 0 in there, that's not going to work, right? And then less than 1. So it's going to be 1, 2. Yeah, there we go. So if you plug 0 in there, you get 0, 0, 0. If you plug 1 in there, you get 1, 2, 1, and it works. Okay, so I just guessed it. I kind of keep ideas in mind. So this is kind of like a slopey thing. 1 minus 0 gives you a slope of 1 in front of that guy. 2 minus 0 gives you the slope of 2. 1 minus 0 gives you a slope of 1. So I mean, there's elements that I kind of have encoded into my brain, and I'm kind of piecing them together to get that equation. But anyways, there it is. Okay, so now I need to go to my my equation, right? And so the way these curve integrals are going to work, you have some f of x, y, z ds, and you'll rewrite this by first substituting in x, y, and z using your r of t. So this is x of t, this is y of t, this is z of t, okay, and you're plopping all those into that formula for f of x, y, z. So it'll look like f of x of t, y of t, and then z of t, and then you're tacking on the magnitude of r of t dt. Okay, and it'll go from 0 to 1 in our case because of the way we set up the parameters. So this thingamajig will go from 0 to 1, plugging in x, y, and z into that x squared minus y plus 3z at the top. I'm going to get now t squared minus 2t plus 3t. Okay, and then times the square root of, and this should be the derivative, right? So that was a major faux pas on my part. This is a derivative because those are derivatives in the arc length formula. This is a derivative. I apologize. I'm so sorry. I'm so sorry, everybody. Okay, so I need the derivative. So the derivative of r of t, right? So r prime of t is going to be 1 to 1. So it'll be 1 squared plus 2 squared is 4 plus back to 1 squared dt. 4, 5, 6, you can factor out the square root of 6 then. And you have t squared plus t from 0 to 1. Oh, oops, I think I'm doing a double integral or something. dt, and then you can integrate each of those using power rules. So you have t cubed over 3 plus t squared over 2 from 0 to 1. So it'd be square root of 6 1/3 plus 1/2. Multiply top and bottom by 2 here, top and bottom by 3 here. So you get 5 root 6 all over 6. Okay, great. So again, example 3 is just kind of a same kind of game. Example 3 here, line integral of x ds, and we have 2 curves this time, so you're going to have to do 2 pieces. So first we go out on y equals x to 1, 1, and then so that's c1, and then c2, it looks like we're going on y equals x squared, right? So the book uses, do they use different parameterizations? No, see, this is some baloney. They force you to do these crazy parameterizations with their weird t goes from 0 to 1. But the truth is, if you go to 0 to 1 all the time, it'll work. Okay, so you don't have to, like we were doing, we had to very carefully make sure that our t values, first it's 0 to 1, then 1 to 2, and then 2 to 3. Then we had to go back and adjust everything. Just make it 0 to 1 each time. You're doing different integrals, so it won't matter. So yeah, so C1 is the curve y equals x. So I'm going to use r of t equals t comma t, and I'll just go from 0 to 1. And then for C2, I need to be a little bit careful, right? It's on the curve y equals x squared, but I'm going backwards. I will go from 0 to 1, but I have to be careful and go 1 minus t, I believe. So 1 minus t and then 1 minus t squared. Let's make sure that works. So when I plug in 0, I get 1, 1. When I plug in 1, I get 0, 0. Okay. I don't know. Get a bad mood every once in a while. So anyways, we'll also always need the derivatives. So I might as well get those out of the way. This will be 1, 1. R prime of t over here. This is going to be negative 1. And then 2 times 1 minus t. I'm so sorry. I got to... So let's rewrite that. Negative 1 comma negative 2 plus 2t. Probably should just FOIL that out. I'm probably going to have to anyways. Then I substitute into my integral. So I'm going to need two integrals. The one for c1. And the integrand is x. And the x component is t. So I just have t, and then times the magnitude of the derivative. So that would just be 1 squared plus 1 squared is 2 dt from 0 to 1. So it's going to be root 2. Integral of t is t squared over 2, and then evaluate from 0 to 1. So it's going to be square root 2 over 2. C2, probably be a little harder, right? So in this case, x is 1 minus t, and then we want the magnitude. Oh, this is where they get you. So 1 plus this thing squared, right? So 2t minus 2 squared is going to be 4t squared minus 4 is 8t plus 4, and then we're going to have to add in a 1 for that other part of the derivative squared. So it would be 4t squared minus 8t plus 5 dt. I have a feeling u sub is going to work this guy, I hope. 4t squared minus 8t plus 5. So du will be 8t minus 8t dt. So dt will equal du all over 8t minus, whoops, what the heck is it? 8t minus 8. Right there, right? Okay, 8t minus 8. And then you could rewrite that to make a nice cancellation, right? So that's dt equals negative 1 over 8 times du all over 1 minus t. And then you get your nice cancellation. Okay, so this would be the integral, pull out the negative 1/8, and then just have square root of u, so u to the 1/2 du. And then that would be negative 1/8 u, let's back sub 4t squared minus 8t plus 5 to the 3/2 times 2/3, evaluated from 0 to 1. So negative 1 all over 12. So I get 4 minus 8 plus 5. So 9 minus 8 is 1. 1 to the 3/2 is just 1. Minus, plug in 0. I get 5 to the 3/2. So at the end, adding in the two parts, from C1 I had root 2 over 2. So my answer is root 2 over 2 minus 1/12 times 1 minus 5 to the 3/2. What did I make? Oh, that's that's not the right one. That's the wrong problem. Yeah, square root 2 over 2, and then they just factored out a negative. Yeah, same thing. Okay, what is this one about? Is it annoying or something? It's a space curve, so it's supposedly different. Okay, it's not much different. Let's look at the problems in the homework with regards to this new issue. So we've kind of already been doing some of these problems. Can we do a space one? Do they have a space one? By space, I mean 3 dimensions, right? I don't think they have any space curves. And then all of a sudden we're back into, oh yeah, you do. Number 7 is one of those. Okay, so let's try number 7. First, you want a parameterization for this thing, and C1 is going from 0, 0, 0 to 1, 0, 0. You know, and the exercise is going to force you to use those weird, instead of going from 0 to 1 each time. Look at that. They're going to force you to get the parameterizations for 1 to 2 and then 2 to 3. So you're going to have a little bit of work to do there. But yeah. Okay, but this one you don't have to worry about that because all the parameters are going from 0 to 1 for each curve. So the first curve, it's just going to be t0, 0 when the parameter goes from 0 to 1. C2, it's going from 1, 0, 0 to 1, 0, 1. So R of t in that case will be 0, 0, t, or actually 1, 0, t, sorry. And that will be a parameterization from 0 to the 1. And then the third one, C3, is going from the point, and I know I have the answer sitting there, but try not to look at the answers. 1, 0, 1 to 1, 1, 1. Okay, so the first component, 1 to 1. So 1 is constant, so you just put 1 there. The second component is going from 0 to 1, so you can put t there. And then the third component is just 1 to 1, so you just put 1. Okay, so we're going to need 3 integrals. The integral du jour is 14x plus y squared minus z. So we're going to need derivatives for all of these. So r prime is equal to 1, 0, 0. Whoops. This r prime is equal to 0, 0, 1. And then this r prime is equal to 0, 1, 0. So each time it's going to be it's going to be multiplied by a square root 1, in other words 1. So you're basically not even going to see that part of the integral. Anyways, the first integral, C1, we're integrating 14 times x. X is t in that case, plus y is 0, minus z is 0, and then times 1 dt from 0 to 1. So that's 14t squared over 2, 7t squared from 0 to 1, so it should just be 7. Okay, go on to the next curve, C2. Integral from 0 to 1 of our vector equation of a line there is 1, 0, t. So it'll be 14 times 1 plus 0 minus t dt. So that would be 14t minus t squared over 2 from 0 to 1. So that would be 14 minus, I guess, just 1/2. So 28 halves minus 1/2 is 27 halves. And then the last curve, 0 to 1, we have 14 plus t squared minus 1 dt. That will be integrating 14t plus t cubed over 3 minus t from 0 to 1. And so that will be 14 plus 1/3 minus 1 is 13 plus 1/3, common denominator. You'll have, I believe, 42/3 plus 1/3, 13 times 3. Whoa. 39, Dave. 39/3, which is going to be 38/3. And then you have to add all 3 parts together. So you got 7 plus 27 halves plus 38/3. And usually I just go the Wolfram and add them up there. Assuming I didn't make any mistakes, which is highly unlikely, right? 27 halves plus 38/3, and I am wrong. So I'm going to have to pause the video and see what I did wrong. Hold on. I think I found it. 39 thirds plus 1/3. Turns out that that's equal to 40 thirds. Who would have thunk, right? Let's go back to Wolfram. Hopefully that'll do it. 40, 203 over 6. 2 over 3 over 6. Sweet. This should be a 40 right here. Okay, sorry about that. Okay, so that's the space version. Then you see something, oh no, what is this? So what this is going to be a line integral over a vector field. So you're sending some sort of particle through a vector field, and you could use this to find the work of the vector field on the particle. Basically, you're looking for the alignment between the tangent vector of the particle and the force field. Okay, so if you see figure 15.13, that's kind of the idea. So in 3 dimensions, you have, let me draw something cooler than what they have. Okay, so kind of this curve, maybe it goes up like that, and then kind of curves up and then over, and then comes maybe down and then over and then around, and then zips over here, and maybe we'll make it go around here and then around here and then up, and maybe connects back like that. Okay, so there's our weird curve in space, and we pretend it's in a vector field, a force field, right? So everywhere in this space is going to be a vector kind of floating about. So way over here, there's a vector maybe pointing in that direction. There's also then on the curve itself, there are velocity vectors, or rather tangent vectors, right? Telling us kind of the direction of travel of the particle in blue here. Okay, so at each one of these tangent vectors, you want to consider the vector from the force field and then consider the alignment between those two vectors, right? And we can measure the alignment between vectors using the dot product. So if you remember, way back in the day, we had stuff like u dot v equaled the magnitude of u times the magnitude of v times cosine of theta. Okay. So the more aligned the vectors are, the cosine function is going to be closer and closer to 1. Okay, and that would be the maximum for the dot product. So yeah, what we're going to do is kind of go along this curve and add up all of the dot products between the force field vector and the tangent vector on the curve, which would represent like velocity of the particle. Okay, and from there you get work, right? And you're just adding all that up. And okay, so you'll have a work increment then. So let me erase this and kind of introduce a section. We're talking about line integrals of vector fields. Okay, so maybe I put it in here, line integral of vector fields. Okay. So we're looking to find the work done on an object moving through a force field, and we're going to be summing up these little work increments. Okay. Remember, work is just force times distance, and for us the force is going to be the dot product between the force field vector and the tangent vector. Okay, so this will equal F dotted with T delta S, where delta S, of course, is a little line segment that these guys will exist on. Okay, we want to put this into an integral then, so work will basically equal the integral over this curve of F dotted with T ds. We need something we can work with, okay, because we're not going to be able to evaluate this thing. So there's a couple ways you could rewrite this. So F dotted with T. So remember what T was, the unit tangent vector? That's really r prime of T all over the magnitude of r prime of T, right? And then ds, we noted above, is really what the magnitude of r prime of T dt. So kind of we can almost put this in the terms of t and evaluate from a to b. But you also notice we can do a little bit of cancellation. If you remember kind of all the weird rules for dot products, you can do a cancellation like this. That'll work. Okay. So what you end up with then is f dot r prime of t dt. Of course, r prime of t dt is just ds at the or dr rather. So remember, what was ds is equal to r prime of t, the magnitude of r prime of t dt. So what the heck is dr, right? So what r prime of t is basically just dr with respect to dt. So this is dotted with dr with respect to dt times dt. So we can effectively write it then as, and I'm losing all my little arrows, the integral of f dot dr. And that's kind of how you usually see the line integral over a vector field written. That's how you'll see it here in their definition. We note the line integral of f, I guess I should say on c, I've been saying over c, is, so starting with this integral, we have f dot dr, and then that will equal, you could say that equals the dot product of f with the unit tangent vector ds, but the working definition ultimately, the integral from a to b of f of x of t, so we'll think in space, y of t comma z of t, dotted with r prime of t dt. Okay, but whenever you see it and they're talking about it in the book, like a question, they're going to write this. But when you go to evaluate, you're going to do this, and you're probably going to forget about this. You know, that formula, unless you could sit there and derive it from kind of first principles. If you're a physics person, you remember the formula for work. And yeah. Okay, but there it is in all of its glory at the end of the day. Let's go to the book and look at some of these, or go to the homework and look at some of these problems. And then we still have more stuff to do. Line integrals, oh, the differential form, that's basically the same thing in a different form. Okay, let's look at number 9. So we want to figure out this line integral. Let me get so it's called the line integral of the vector field f on c. Okay, I want to get that. Seems like so the vector field is 9x comma 6y. The curve, they're nice enough to give it to you, is t comma square root of 4 minus t squared. And then the parameter is going from -1 to 1. My brain is not doing what I tell it. My hand is not doing what my brain tells it to do. I don't know why. Anyways, let's go to the integral then. So we're going to rewrite the integral, replacing f with f of x of t comma y of t. So I'll have 9. Then I need to use this thing for x. So that's t comma 6 times y. So in this case, 6 times the square root of 4 minus t squared. And then dotted with the derivative of r. So r prime of t is going to be 1 comma 1/2 times 4 minus t squared to the -1/2 times -2t. Of course, I run out of room. So it's dotted with 1 comma 1/2 times -2 is 1, -1, and then there's t there, all over the square root of 4 minus t squared. And then Yeah, then dt, right? Because that magnitude thing kind of cancels out. You don't have to worry about it here. Okay. All right. So find the dot product and integrate from -1 to 1. So right. So I have 9t minus 6t, right? Because 4 minus t squared square root of cancels. So that's pretty easy. Integral 3t dt. So that will end up being 3t squared over 2 from -1 to 1. And of course that would be 3 halves minus 3 halves, which is 0. Okay. A lot of 0 answers floating about. Find the work done by the force field F on the particle moving in the given path. So it's problem 11. Force field is x squared comma negative xy, or my curve. Looks like a monster. I guess we have cosine cube t, sine cube t, and we want our t, well, x is going from 1 to 0, so I want t to probably go from like, so it's going from 1, 0 to 0, 1. I need to figure out my t value. Okay. So if I start at 0 and then go to pi over 2, that'll do it. Right, so if I plug in cosine of 0 cubed is just 1 cubed, which is 1. Cosine of pi over 2 is 0. 0 cubed is 0. Sine of 0 is 0. 0 cubed is 0. And then sine of pi over 2 is 1. And 1 cubed is 1. So, okay, so that works. That's my r of t. Okay, so I need also its derivative, r prime of t. So power rule and then chain rule. So I mean -3 cosine squared t sine t, and then 3 sine squared t cosine t. Dandy. All right, so my integral then will become the integral from 0 to pi over 2. I need to rewrite my force field function with the components plugged in. So I'll have 9, I guess, cosine to the 4th t, sine squared t, and I'm starting to freak out because this looks like a nightmare. The second component would be -9 cosine cube t sine cube t, and then times r prime, or dotted with r prime, -3 cosine squared t sine t, comma, and I'm going to need a little more room, comma, 3 sine squared t cosine t dt. Okay, let's go ahead and figure out what the heck that is. So this times this is -27 cosine to the 6t sine cube t, and then this times this is -27 sine to the 5th t cosine to the 4th t dt. Oy, oy, oy. Is there anything? You know, I'm just gonna have to do u subs, I guess. Push back and then u sub. So I'll let u equal cosine. Really? I don't remember it. This guy being that difficult. You know, seems like I probably made a mistake. Let me pause the video and make sure before I go down a rabbit hole. Okay, I see the mistake I made. I put in r prime in for x and y here, so these guys are wrong. Sorry about that. I'm glad I stopped and looked before I went any farther. That's all I gotta say. Alright, so the first one, putting in cosine cubed, right? So I'll make that a cosine to the 6t, and then it'll be negative sine cube t cosine cube t. And then now taking a dot product, you get -3 cosine to this 6, 7, 8t sine t, and then I guess minus 3 sine to the 5th t cosine to the 4th t. Okay, for the first guy, u sub, right? It's u for cosine t. The derivative will be negative sine t dt. So this portion will go away, and you'll just have some integral of u to the 8th, but there'll be a negative floating around as well, so that'll become positive, and then du, and then minus. So this time on this guy, you got to push back one factor of sine. You'll end up with 1 minus cosine squared t squared times cosine to the 4th t times sine t, right? And then you're going to let u be cosine again, and du will be negative sine, so this part will go away, and you'll end up with a negative floating out, so this will become plus 3 integral of 1 minus u squared times u to the 4th du. So this will become 3u to the 9th over 9 plus 3, and then you got to FOIL this out, so it'd be 1 minus 2u squared plus u to the 4th times u to the 4th du, and then this will become 1 u to the 9th over 3 plus 3 times the integral of u to the 4th minus 2u to the 6th plus u to the 8th du, and then this will become u to the 9th over 3 plus 3 times u to the 5th over 5 minus 2u to the 7th over 7 plus u to the 9th over 9. You have to evaluate eventually. Does any of that cancel? Well, these guys are like terms. This one and this one. That would be 1/3 plus 1/3 is 2. But they don't have the same u values, do they? Yeah, they do. They're both cosines. Okay, so you get 2 cosine to the 9th power x all over 3 plus 3 cosine to the 5th power x all over 5 minus 2 cosine to the 7th power x all over 7 plus, well, that was it, right? Did I get my 3 distributed? 3 on to this one. I missed the second one, so it'd be minus 6 cosine of the 7th, and then the last one I combined already with the first term. All right, and then we have to evaluate from 0 to something. I think we said pi over 2. Okay, when you plug in pi over 2, cosine of pi over 2 is just 0, so the whole first thing is 0, and then plugging in 0 you get 1, but it's a minus, right, because you're minusing the bottom antiderivative evaluated at 0. So it'll be 2/3 plus 3/5 minus 6/7, which totally seems wrong. And that, I mean, you could get negative answers for these. That's not the issue. It's just I did it, yesterday. Oh, it is negative. All right, well, I stand corrected. I don't think it's, oh yeah, it's because all the denominators are relatively prime. So that was very kind of the makers of this problem. Plus 3/5 minus 6/7, 43 over 105. Is that right? Yay. All right, so they can be quite challenging at times, and sometimes you really have to dig deep to get the integral done. Anyways, the next two problems you see are looking strange, right? But they are actually just these line integrals of a vector field over on a curve. Okay, so it's called the differential form. That's the last topic we have in this section. So let me find my Roman numerals. And I haven't forgot about our quiz thingamajig. My Roman numerals, I think, went from 1 to 2, back to 1 again. So let me fix that real quick. So this would have been 3. and then we're on section 4. Okay, so line integral in this other form, this differential form. So again, you could start with our integral of f on this curve C. Okay. Sometimes I forget the little arrows. I mean, I'm not going to beat myself up over it, because I was watching an MIT video the other day, and the guy never used arrows. So I'm like killing myself putting little arrows over everything, and they don't even do it at MIT. So I don't know. Anyways, so what is this thing? We want to rewrite it in a different form, okay? And in particular in terms of x's and y's and stuff. So f we could write as m n, and then you put it in three. We're just doing the two-dimensional version for the differential form. Okay, two-dimensional only, and then the derivative of r is the same as the derivative of r with respect to t times dt. Okay, so it's dr is the same as dr with respect to t dt. Okay, so I'm going to kind of rewrite this part of it. So I have the integral of m comma n just dotted with well, no, that's dt. Dotted with, how do I want to do this? R prime of t dt would be x prime of t, or if you would rather, dx over dt is probably the way we're going to be able to pull this off, comma dy over dt. Right? And then you can kind of think of it as multiplying by dt. I mean, I'm sure that for technical reasons or theoretical reasons it's not correct, but you would have dx comma dy like that. And then if you got the dot product, oh my gosh, I just lost where I was. I had a weird button on my mouse and now I have no idea where I am. Okay, I think I'm back here somewhere maybe. Yeah, there I am. Okay, sorry about that. Okay, so what the heck is this thing then? This is m dx plus n dy, and that is going to be our differential form that we want. So it's really just the plain old line integral of a vector field over a curve, rewritten in terms of x's and y's. Okay, so that's what you see there on the right. Let's look at some of the problems, and of course we want a video quiz here. So let's make number 14 our video quiz. And this is a second video quiz in video quiz set number 9 from 15.2. This is problem 14. Okay. Okie dokie. So have my integral 2x minus y dx plus x plus 9y dy. I mean, there's several approaches you could do to this. You could convert everything in the terms of t. Sometimes you're actually going to be able to keep everything in terms of x. I usually just convert everything in the terms of t and then go from there, right? So the curve is going from 0, 0 on the x-axis, 0, 0 to 0, negative 9, and then it's going to go from 0, negative 9 to 2, negative 9. So there's basically, I guess, two curves we need to deal with. C1, I'll say r of t is going to be 0 and then negative 9t, and the parameter is running from 0 to 1. And then C2, r of t is going to go from we'll say 2t, so I'll run the parameter again from 0 to 1. So at 0 it's 0, and then at 1 it'll be 2, and then negative 9. Okay, so it's always just negative 9. And then I can kind of rewrite my original integral. Okay, so the bits and pieces I need the x of t for this part, the y of t for that part, and then dx. So for the dx and the dy, I need to get the derivatives of the r of t things. So I need r prime of t is going to be 0 comma negative 9, and here r prime of t is going to be 2 comma 0. Okay, so rewriting all of this to use first curve 1. Okay, so curve 1, I have 2x, so that'd be 2 times 0. So a lot of times a lot of it will just be 0. And then minus y, so minus negative 9t is plus 9t, times dx, and that is this guy right here, so that's 0. That's nice. So that whole thing will be 0. And then plus x, so that's 0, plus 9 times y, so that'd be minus 81 times t, and then times dy, and dy this time is negative 9. Okay, like that, and then dt. Okay. Okay, so the first portion is just 0, and then you have looks like 729t dt. So it'd be 729t squared over 2, evaluated from 0 to 1. So it's just going to be 729 all over 2. Okay, now I need to do the same thing for C2. Okay. So I have the integral then so again, now I'm using all this junk, right? So 2 times x is going to be 4t minus negative 9, so plus 9 times dx, which in this case was 2. And then plus the other guy, which is just going to end up being 0, right? It's going to be a bunch of stuff times 0, which is just 0. So I don't need to worry about it. Okay, so this integral will then be 8t plus 18 dt. Integrate 8t squared over 2 is 4t squared plus 18t. Evaluate from 0 to 1. That'll be 4 plus 18, which is equal to 22. So 729 over 2 plus 44 over 2 should be our answer. 729 plus 44. 3 carry the 1. 4, 5, 6, 7. 773 halves. I'm hoping. Oops. Halves. Let's make sure. Yeah. Okay. So you can play that game. Just turn everything in the terms of t if you want to evaluate it. But like I said, there are some examples. I think one in the book where they can just go ahead and evaluate everything in terms of x. It was this example. So if you want to read through that example, every once in a while, that's possible. Okay. Okay, let's just leave it at that, and we'll call this video over. It's been an hour, so that's good enough. And thank you for watching as usual, and I'll see you next time.